We're going to continue on with our discussion of 1.1 Preview 2 Calculus, so call this Part 2, and we're going to talk about the area problem. So in the other video, we talked about the tangent line problem and how we can't find the exact tangent line yet, but we can approximate it. We're going to have a similar thing with the area problem. So first of all, let's explain what the area problem is. When we talk about the area problem, we're talking about area between a curve or a function and an x-axis. So as long as we have something that is, like for instance, a constant function, we don't have a problem because the area between the function and the x-axis will just simply be the area of a rectangle. Or if I have something that is linear like this, I don't have any problems because I can find the area of that area using the trapezoid formula. If you remember, the trapezoid formula is 1/2 h b1 plus b2. We will be using trapezoids at some point. Typically when we use trapezoids, like if we were going to do the area of that, the formula I'll tend to use is 1/2 delta x, because the height ends up being the change in x, and then y1 plus y2, as in y1 and y2, those end up being our parallel bases. So we can find the areas under those functions no problem using the skills we already had. Just like we could find the rates of change of something that's linear, we could find the rates of change of things like that as well, okay? The problem comes if we have something that is curvy. So just like we had before, if I had something that was curvy and I was doing a tangent line, I could approximate that using slopes of secant lines. What we're going to do here, if we want to find the area of something like this, is we're going to cut it into various shapes. Okay? There's basically, I'll tell you, there's basically two different shapes that we're going to be interested in. Trapezoids, where we're just going to connect the dots. Today I'm going to talk about rectangles. There's two different types of rectangles we'll use. Actually, there's three. There's the right hand approximation. So for each one of these rectangles, we basically use the height of the right of the rectangle. So that would be a right hand rectangular approximation. Down the line, we'll also do left hand approximations. So the left hand would look like this, etc. And we will do midpoint approximations as well, which kind of split the difference between those two things. So let's do an example. Okay, I'm going to once again use x squared as our function, make our arithmetic quite easy to deal with. So we're going to do the area between the function x squared and the x-axis, and from the point 0 to 2. So we're talking about this, all this area in here is what we're going to approximate. I don't want you doing things with circles and stuff like that. That is not a method we'll be using, even though if you're like, oh, well, I could get the curves better that way, that's not something we'll be doing. There'll be basically two shapes we'll be using to approximate these areas: rectangles and trapezoids. So I'm going to start off by approximating this using 4 right-hand rectangles. Right endpoint rectangles. Okay, so the 4 right-hand rectangles, so we have 4 rectangles. Okay, and right hand just means for each one of these rectangles, instead of using the point on the left or the midpoint, we use the right hand endpoint of that rectangle. That's all that means. Now you'll notice that this is clearly an over approximation. Okay, so we do know that this isn't necessarily going to be a good approximation, but it's a start. All right, so now what I'm going to do is just find the area of these various rectangles, which is quite easy. So we have 4 rectangles here. I want to point out that the width of each of these rectangles, which we'll call delta x, is going to be 0.5, because if you take 2 and divide it by 4, you're going to get 0.5. 2 as in 0 to 2. Okay, so now the area of the first rectangle will be 0.5 times, and we're going to take 0.5, and we're going to plug it into our function x squared. Okay, and we're going to keep going like this. So that's the area of our first rectangle done. Area of our second rectangle, 0.5, and then we're going to plug 1 into, now let's just write it like that, a little cleaner. We're going to plug 1 into that, so that gives us our second rectangle. Our third rectangle, our width once again is 0.5, and we're going to get the height of this rectangle by plugging 1.5 into our function x squared. And then finally, our last rectangle, we're going to get multiplying the width, 0.5, and then the height of the rectangle if we take 2 and plug it into our function, squaring it. Now, the one thing I'm going to do here to make this a little bit simpler, anytime we use the same rectangle shapes throughout, we don't have to keep writing the 0.5, obviously. That does not change. So I can factor out the 0.5, leaving me with a nicer expression. So anytime, this works anytime our shape doesn't change. Down the line, we will sometimes deal with shapes that do change. Now I'm just going to calculate this in my calculator real quick. So 0.5. You can follow along if you want. I know it's kind of boring to watch me push buttons. And what we get is we get 3.75. So that's our approximation. So for rectangle approximation is going to be 3.75. Okay, so like we did with the tangent line, if you remember, we started with a secant line that went from 1 to 1.5. We then did a secant line that went from 1 to 1.1. So we can get a better approximation. And this one, the way we're going to do that is a little bit different. So instead of doing 4 rectangles, we're going to go ahead and do 8 rectangles. Okay, so now we are going to go ahead and do the approximation. Before we did 4 rectangles, now we're going to do 8 rectangles. Now, once again, you can see that the approximation is going to be over, but if you compare it to before, that difference is at less. The more rectangles we have, the more it's going to closely follow the contours of that curve. So if you think about the tangent line approximations, the closer we got those 2 points together for the secant line, the better that approximation was. The more rectangles we choose here, the better approximation this will be. So we're going to stop here with 8 because this one is a little bit more time consuming as far as the math goes. Down the line, we might do more. So for instance, if I use 20 rectangles here, we'd have a very good approximation, or 100 rectangles. That would be better still. And then eventually we'll get to the point where we can find the exact using calculus. Okay, so 8 rectangles, once again, the shapes aren't changing here, so let's figure out what the delta x here. So if I go 2 minus 0, that is 2, divided by 8 this time, that's going to be 0.25. So since I know the shape isn't going to change, I'm going to save myself some time. The width for each one of these is 0.25, and then I'll just count the various heights. So the first one would be 0.25 squared plus 0.5 squared plus 0.75 squared plus 1 squared plus 1.25 squared plus 1.5 squared plus 1.75 squared. And let me write down here and make sure this shows up. This would be plus 2 squared. One thing you want to do, because it's easy to miss one, is just count. We have 8 rectangles, we should have 8 heights of rectangles. So 1, 2, 3, 4, 5, 6, 7, 8. There you go. I believe I already have this calculated. Let's see if I can bring it up. And there we go. So 8 rectangles, we are going to get 3.1875. And we would assume that this is a better approximation for the exact. In fact, I can tell you what the exact is because I know the calculus. So let's see what the exact is going to be so we can compare this. And then, of course, throughout the course, we'll figure out the exact is actually 2.6 repeating. So these aren't great approximations, But if you went more rectangles, you would get better approximations. So that is our preview. Our two big problems, the tangent line problem and the area problem. Really, when it comes down to it, calculus falls into one of those two categories. Those are the big ideas.